In this video, we describe an interactive visual analytics system for exploring, monitoring and forecasting road traffic congestion. In the city, there are 128 CCTVs, 201 loop detectors, and 189 DSRC detectors. By performing task analysis with domain experts, we derived 5 task requirements. Here, the first and fifth requirements are for retrospective analysis, the second requirement is for real-time congestion surveillance, the third requirement is needed for both retrospective analysis and real-time monitoring, and the fourth requirement is for predictive analysis. There are retrospective analysis and real-time forecast modes in our system. The left part in the filter menu is for replaying historical congestion data. The right part is a menu for the analysis mode. Our system allows users to change update and time intervals in replaying past congestion. In the analysis mode, users can load and filter the data by days of week, weather, vehicle volume, and vehicle speed. First, we visualize congestion using VS River. VS River used an 15-minute time interval and updated every 10 seconds in the replay mode. The user first changes the time interval to 30 minutes for replaying. Our arrow visualization helps users investigate congestion causes and propagation directions. Here, we see that the congestion started from the road of P1 and P2 and then propagated to the road of P3 and P4. When many roads were involved with congestion, B-spline algorithm is used for visualization. Different arrow colors represent different degrees of congestion severity. In the first study, we present how an analyst in a city hall uses our system for find characteristics of city congestion. Here the analyst uses the analysis mode of the system. First the analyst selects the full range of 2017, and filter by max speed of 40 km per hour. Table view can be sorted by road name, average speed, and estimated travel time. This shows how an analyst interact with the table view for finding specific roads. Then the analyst looks at the calendar view. Here holidays are shown with black outline boxes and average volumes are shown at the end of each row and column. The analyst sees that less congestion existed during holidays and weekends in both streams. Here, it seems there was a lot of speed difference in upstream and downstream, according to the color of the calendar view. But it turns out that there is almost no difference between the streams, as shown in the tooltip. Then the analyst investigates most congested areas using the snapshot view. We see many factors contributed to the congestion of S1, including highway entrance, residential areas, a university, a traffic circle and a bridge. The main causes of the congestion in S2 could be the traffic circle and business district, because vehicles from the industry complex and downtown use this traffic circle. There always is large traffic volume in downtown area, S3. After an industrial complex was developed above S4, new traffic for commuting and logistics were generated in S4. The analyst can move around the important areas by selecting the safe areas in the snapshot view. Analysts can also select road directions for visualization. Here, the analyst selects several roads in the areas to perform an in-depth analysis. Here the analyst sees the area S2 and S3 were impeded in the evening time, while S4 was impeded most of the time. Next we describe how an analyst uses our system for investigating impacts of a city congestion improvement project. Here the analyst sets the time range from January to April to investigate congestion conditions of the area before the project began. This area was one of the main industry complexes in the city. Here the orange road is important, because it has affected other roads' volume. In order to investigate the result of the project, the analyst selects the time range from May to December. Note that the project began in May and was completed in October. Here the analyst can identify changed congestion condition on a road from a slow condition to a normal condition. Pixel visualization can provide detailed information. From the pixel visualization, the analyst sees an improved congestion condition in October. The next task is to find a candidate road whose congestion conditions can be improved with the project. Here, the analyst sees several candidates of congested roads with VS River. The volume on Road A is mainly for going to another city. The volume on Road D is less than other roads. The Road C is located inside the complex, which implies only few factories would benefit with the project. Road B seems to be a good candidate, because it is located at the entrance of the complex and has the largest number of connected roads. To analyze daily pattern of this road, the user uses pixel visualization and finds that this road is usually congested in the daytime. In the last study, we show how congestion reporters in a radio station utilize for broadcasting city congestion. In the real-time mode, the black box road is congested in both directions and our system predicts the upstream road will be congested after 15 minutes. Here we see our system predicts that congestion conditions in both streams will be better at 6:04 p.m. Reporters can make their script for broadcasting more specific and concrete by using congestion forecasting. Our system provides estimated travel time, which also helps the reporters make their script more concrete with specific numbers. Chronic congestion tends to repeat at the same locations. By saving those chronic congestion points, the reporters can quickly review congestion conditions in the points. Here, the reporter selects for chronic areas, checks the CCTVs, and saves current selections with the name of 2 p.m. By doing this, the reporter can reload the saved 2 p.m. session for everyday 2 p.m. broadcastings.